what we're going to do today is we're going to introduce you to the concept of vector math. Now, you may have heard the phrase before, vectors. What are vectors? Well, before I can go to vectors, I have to talk about other types of measurement as well. Everything we do in science is a measurement. There we go, sorry. If it isn't measurable, it is not scientific. That's really what it comes down to. If you cannot measure it, it is at best an anecdote. It is not data, okay? And so in the physical sciences especially we see this, but of course biology does as well. Some of the social sciences have measurements as well. The point I'm trying to get at is this. Our measurements can be classified into two different groups. One group is called a scalar. A scalar is a measurement that has magnitude only. Okay? For example, mass. Mass has magnitude only. I've got a jug that's 5 kilograms. That's an amount. It doesn't have any direction to it. I don't have a jug that is 5 kilograms to the left. You see where I'm going here with that? Okay? Speed is a scalar. You want an example of that? Take a look. Can you look inside your car, look at your speedometer and see how fast you're going? Yes, you can. Can you tell where you're going from that? No. Is there any negative numbers? No. There is no negative speed. There is no negative speed. There's negative velocity, but negative velocity means something different, doesn't it? Okay. What about volume? Can you have a negative volume? Not really. I mean, there may be times when we think about it in that way, but you get the idea. Most scalars really don't have a negative amount, if you will. But something which has magnitude and direction is called a vector. A vector is a quantity that has magnitude and direction. If you're having trouble remembering that, go watch Despicable Me. After all, what was the name of the villain? Vector. I mean, the bad villain, not the nice villain, the bad villain. His name was Vector because he did evil with magnitude and direction. And I'm so glad I don't have a camera on me when I did that. You know, direction. Okay. Oh, yeah, okay. And now I'm visualizing the squid gun. Okay, let's get back to this. We already have 3 vector quantities. You know they're vector quantities because we've dealt with direction on these quantities before. Position, velocity, and acceleration. We've talked about what position and negative position would mean, what velocity and negative velocity would mean, acceleration and negative acceleration would mean. We've done our motion in one dimension, along a line, going backwards and forwards to the front of the room and the back of the room. But if you're watch a football game, that one-dimensional game that's played on a two-dimensional surface, you got velocities going in different directions, don't you? So what we need to do is we need to be able to do math using vectors. So first kind of math is going to be addition. So here's my question for you. Vector A has a length of 15 meters pointed to the east. Vector B has a length of 10 meters pointed to the northeast. What is the sum of vector A and vector B? I will give you one hint. I have protractors and rulers up here. Enlightened, but you will become enlightened. What's the first thing I ask you guys to do whenever we solve a problem? Draw a picture. This lends itself directly to drawing a picture, doesn't it? Because after all, what we're trying to do is we're trying to add 2 displacement vectors. In essence, it would be the same thing as if I was standing at a point. I would stand at a point, and then I would walk 10 meters, I would walk 15 meters to the east. So I go trudge, 15 meters to the east. Then I make an oblique turn and go 10 meters to the northeast. Do you see how A follows B? Then all I have to do is look at where am I now compared to where did I start. Now already, that should re-enlighten some of you as to what the triangle should look like, yes? Okay, but let's look at the triangle. What am I talking about? First, I need to draw the two vectors. Here's what I'm going to do. I'm going to use a scale. I told you that the hint was I've got rulers and protractors. Okay? So why not draw it to a scale? 1 meter is 1 centimeter. If I do that, how long is a 15-meter line going to be? 15 centimeters. How long is a 10-meter line going to be? 10 centimeters. Do you see what I'm talking about here? It's what you do when you're plotting on a map. Do you see what I mean? And now all of a sudden the light bulbs are starting to come on. We have our two lines here. Vector A, 15 meters due east. Vector B, which is 10 meters to the northeast. To draw vector B in the right direction, I have to use a protractor to get that 45 degrees north of east. And now you see where the directions come into play. The next step then is if I'm going to add A and B together, I've got to put the tail of B on the head of A. Can I do that? Can I move the vector? Can I draw another vector that's 10 meters in the same direction? The answer is yes. Very important point here. Any two vectors that have the same magnitude and direction are equal vectors. So 10 meters to the east, starting from Marion, is the same thing as 10 meters to the east, starting from Birmingham. The vectors themselves are still the same. Following along? Everything makes sense there? Okay, excellent. So now I redraw A, 15 meters to the east. I redraw B from the head of A, 10 meters to the northeast. Next, I want to find the sum. That is to say, where did I end up compared to where I started? So I just draw this line here from the tail of A to the head of B. There's my sum. That's A plus B right there. How do I find the magnitude and the direction? Excuse me? What arrow? So what I'm sorry, what are we going to do? How? Measure directly. Exactly right. Measure directly. You've got a scale. 1 meter is 1 centimeter. So you measure how long that line is, and they'll tell you how many meters it is. And then you use a protractor to figure out what the angle is. And the angle is going to be from the direction of A, from east. And so we see that when we measure directly, it's 23 meters long at an angle of 18 degrees north of east. You following along now, guys? You can't say northeast. That's a specific direction. You can't even say east-northeast. East-northeast is 22.5 degrees north of east. You see where we're going here, guys? Everything makes sense? Think we can do this now? Good. Let me give you a harder one. I want you to add up A, B, and C, please. I'm walking around and I see enlightenment. Not necessarily the religious experience, but you guys are going in the right direction. All right. Now you see how handy a protractor and a ruler are, yes? Especially if we're adding vectors together. The first vector, we're going to go ahead and draw vector A. Oh, and by the way, an interesting exercise. What if you change the order for addition? Do you still end up at the same place? I'll leave that as an exercise for later. But let's start off. There's vector A pointing to the east, or pointing to the west. From there, I'm going to add vector B, which is pointing due north. From there, I'm going to add vector C, which is pointing to the northeast. Okay, notice my little check. A is 10 meters, B is 20 meters, and C is 30 meters, so C must be 3 times as long as A. We're going to be working on some problems where you'll be able to estimate them and be able to see relative sizes. Anyway, the next step then is to draw the line from the tail of A to the head of C, and that gives us A plus B plus C. Last step then, real simple, all we have to do is measure. Take out the ruler, measure according to our scale. We end up getting 43 meters at an angle of 75 degrees to the north of east. Now, two things. Number one, the direction. Some of you may have chosen to go 15 degrees east of north, and that would have been correct as well. Notice I put in the direction. What I mean is this. North of east means I'm going to point to the east, and then I'm going to rotate that angle to the clockwise direction, to the north direction. That's why I say north of east. You could also say east of north, in which case your starting direction is north, and you're going to rotate in the counterclockwise direction, in the eastward direction. Do you see where we're going here, guys? Now, generally, it's really kind of weird. It depends on all the context. In math, in our math classes, our reference line is usually positive x, and we rotate for positive rotation in the counterclockwise direction. In navigation, our reference line is due north, and we rotate from there in the clockwise direction. So again, context is everything. Make sure when you're doing your homework that you read the homework, because it'll tell you where you're measuring your angles from. Okay? All good? Good. I got another problem for you then. Yay! Don't you love it when I give you problems? Easy to solve, right? Okay. How about this one? Vector A, the same two vectors. A is 15 meters to the east, B is 10 meters to the northeast. What is A minus B? So the real question here is, how do we subtract vectors? We know how to add vectors, so how do we subtract vectors? And the answer is by adding them. Now that sounds kind of weird. Let's look at it this way. If I take a look at A minus B, it's the same thing as A plus minus B. Just like in algebra, if I take x minus y, it's the same thing as x plus minus y. Okay? Everything makes sense there. So what we need to define is, what is minus b? Mathematically, minus b, the opposite of b, is whatever you add to b to get to 0. Or another way of putting it, what do you add to the vector b that gets you back to where you started from? Well, that means we need to add a vector that gets us back to our starting point, which is just the same distance, but in the opposite direction. So all we need to do to draw a vector minus b is just move the location of the head. You see where we're going here? So where b is pointing to the northeast, minus b is pointing to the southwest. Now all we have to do is to add a to minus b. And so we have our drawing for A, our drawing for B. Let's go ahead and draw minus B, which is going to be pointing to the southwest. And now we're going to put the tail of minus B onto the head of A to get us that picture. A number of you are actually getting there, okay? And again, I like these exercises not because I want to see you guys spitting in the mud and all that. It's because you guys are trying something. And when you guys get it, it sticks. And when you guys don't get it, you know what doesn't work, and you're ready to figure out what does. Okay? I mean, what was it I saw a long time ago? Anybody who's good at something at one time had to be bad at it? Okay. So, not a problem. So we're going to put the tail of minus b onto the head of A. That means we need to draw the resultant vector, A minus b, and then break out the ruler and the protractor to get 11 meters at an angle of 41 degrees south of east. Now, let me talk a little bit about this, because I was looking around, and a couple people had the distance of 10 meters. And that's okay, because you are limited in your measurements. I'm not saying, what I'm saying is you're limited by the precision of your instruments. Okay? If we take a look at the protractors, how many digits can you get on your protractors? Seriously? 2 digits. You can get down to the degree. Getting down to the 10th of a degree, maybe if you're really eyeballing it tightly, but probably not. On the other hand, if you're using a whiteboard pen, the whiteboard pen itself is about 3 degrees wide, so it doesn't matter about getting down to the 10th of a degree then, does it? Okay. And what about the rulers? Well, if you look at it, you can get down to the centimeter, maybe you can get down to the 1/10 of a centimeter with the millimeter marks, but still you have a limit to your precision, don't you? Well, what happens if I give you a problem where I give you 5-place precision? I give you vectors that have 5 decimal places in each of their numbers. If we use this method, we would lose precision, wouldn't we? Okay, because we would not be able to preserve 5-place precision when we only have 3-place instruments. Okay, so how do we go about doing that? That's what I'm going to talk about Wednesday, where we do an algebraic method that will allow us to preserve the precision of our measurements. Now, I do want to give you one example of where subtraction does come into play. I like doing this only because it's this is kind of a useful skill. Okay? Now, anybody who's going to go into maritime navigation or into aviation, you're going to run into this. Now, I'm going to look at it from an aviation perspective, but it's easy enough to translate. Okay, so let's start off with, I take a fix and I'm located at that point right there. I want to go to this point right here. There's my airfield. There's my gas, there's my food, there's my bed. Okay, I want to go there, which means I want to travel along this line. Okay, that is my desired course. Is that how I'm actually going to go? Well, it depends. First off, I'm going to go ahead and draw a velocity vector because I'm going to use the velocity vector to figure out how long it's going to take for me to get there, right? If I know the distance and I know the speed, then I can figure out the time, right? So I'm going to draw a velocity vector. This is going in this direction, and this is my heading. This is the direction I'm going to point my airplane. That would make sense, right? It's over there. Point the airplane in that direction. One more little detail, because it's a velocity vector, I need to add the true airspeed. How fast am I moving through the air? Driving in one of these little Cessnas, I'm probably doing about 100, 120 knots. Driving in my airplane way back when, we'd do about 350 knots. Of course, y'all, those of you who want to go hair on fire, tack air, you're sitting there zipping along at about 700, 800 knots. Then you get the guys who are in the SR-71s. What's your true airspeed? 1,500 knots. Okay, let me get back to this. So this is how fast you are moving in the air. But what is the air doing? The air is moving as well. If you're standing on the ground, what do we call that? No. If you're standing on the ground and the air is moving, what do we call that? Wind. So we need to take a correction for the wind, because the wind is going to take, I'm pointing to the east, but if the wind is blowing from the northwest, it's going to push me, isn't it? So there's my wind, and therefore I need to add those two, and that gives me my track and my ground speed. That's where I'm actually going. And if I ran that vector out, this is where I would actually end up. I don't want to end up there. That could be a bad place. People don't like me there. I don't know. I owe money to somebody. I don't know. So anyway, what I need to do then is I need to correct for that wind. Now, those of you who have done aviation know what I'm doing, which is calculating the wind triangle. Here's how it works. This is the actual direction I want to go. So this is what my track should be. What I'm going to do is I'm going to subtract from that the wind, and that's going to give me my heading. And this angle here is called my crab angle. You following along now, guys? And we have all sorts of little techniques, some computers that'll do it for us. Of course, we have to take into account what happens if the electricity goes out. Then we have to break out flight computers. And that will do all this stuff too. E6B or MB4. That's the other type of flight computer that I used to use. Okay? So as you can see, this is vector subtraction. So vector subtraction, vector addition, both things we need to do. All right. Any questions from y'all? All right, then we'll talk more about this on Wednesday, and I will see some of you guys on tomorrow.